All right, let's do it, huh? We're going to talk about two things today. We're going to talk about stability from an I/O perspective, input-output. And then we're going to talk about state feedback and this is a method, let's say A, to stabilize unstable systems. And B, to reshape system dynamics. And I'll put this in here as change the A matrix. We need some quotes. Okay. I'm going to be pretty brief about the stability stuff. Just kind of describe what's going on, some of the ideas that are there. What we're going to do is to connect these notions of input-output stability back to stability of a state space realization that's minimal. And then we'll then go back and think about these things in terms of the state variable realization, where we get to do all this matrix algebra type approaches to the solutions. Okay. So here's some definitions. Suppose I have a time, an input system, an input-output description for a system, either via its weighting pattern, g of t comma tau, and I'll put those two arguments in there, t and tau, so we can allow for time-varying systems. If the system is time invariant, we can think in terms of its transfer function, g of s, which at one time we labeled as g hat of s to avoid confusion with the weighting pattern g, but we'll assume we can kind of keep straight that these are two different functions. All right? So what we do is say that an I/O system with weighting pattern g of t comma tau is uniformly bounded input, bounded output stable. Should slow down, huh? Bounded output, or BIBO, stable. If there exists some value eta that's non-negative and finite, such that for all t0 and functions u of t, input signals u of t, that the supremum over all t bigger than or equal to t0 of the output y is less than or equal to the supremum over all t greater than or equal to t0 of u of t multiplied by this constant eta. So it's a scale factor eta that uniformly over all possible choices of the input signal, that if I have this is a bound on the input. that if my input is bounded by some amount, that the output also will be bounded. And I can determine the bound on the output as a linear multiple, just a multiple of the bound on the input. All right. So this is a characterization of, and you can think of it as, typically you think of this sort of thing where if this is u of t, and u of t is kind of going up and down, and you might have, this is the, if you're going between some value a and minus a, that the size of u of t is staying between, is always below a. If you take the absolute value of u of t in terms of a scalar, if I have a vector function, I can look at the vector norm. So these are just vector norms. and that if I have some bound on the input, then I get a bound on the output, and that bound on the output can be expressed in terms of how big the input is. Okay, so I stapled this sheet on here. It's not going to stay. So in this sense, this is just the normal sense of bounded input, bounded output stability that we're familiar with. If the input's well-behaved, the output is well-behaved too for systems that we like to call stable. So now what we can do is characterize the stability properties of a system in terms of the descriptions of the system dynamics. So if I have the weighting pattern, this is the weighting pattern of a uniformly bounded input, bounded output system, or bounded input, bounded output stable system, or we can say in shorthand, the weighting pattern itself is uniformly bounded input, bounded output stable, by which we mean that the system with which it is associated has that stability property. This is true if and only if there is some non-negative value rho such that when we integrate the norm of the weighting pattern over time tau from t0 up to t, that this is going to be less than or equal to that value of rho for all t greater than or equal to t0 and for all t0. Okay, this, I should point out, is a matrix norm. The weighting pattern g of t comma tau is a p by m matrix function of those two variables. We could spend time talking about matrix norms that are induced by associated vector norms. But basically, if I take, this is a p by m matrix, and so I can multiply m vectors by this p by m matrix and get p vectors. And we have a notion, let's just take the normal Euclidean norm for the m vectors, just sum up the square values of the entries, or the absolute value squared in the case of complex stuff, and then do the same thing for the p vector, that's the output. And the matrix norm essentially is the largest that the ratio of the output vector norm to the input vector norm can be. Okay. And this matrix norm for that sense is equal to the square root of the maximum eigenvalue of G multiplied by its transpose. And that also is equal to the square root of the maximum eigenvalue of G transposed times G. So if I take a matrix and I multiply it by its transpose, or I take a matrix transpose and multiply it by the matrix itself, and if this is a complex valued matrix, we would want these to be, the Hermitian operation as opposed to the transpose operation. And this is equal to the maximum over all vectors u whose norm is equal to 1 of the norm of g of t comma tau times u. Okay, that's the vector norm on the p by 1 vector that comes out. We just multiply this times any vector of norm 1. The largest that can be is our matrix norm. Okay? And although we're not going to do it, it's not terribly hard to connect that property of the weighting pattern to the definition of bounded input, bounded output stability that we posed. Okay, so we can also connect the stability properties of an input-output system back to the stability properties of a state variable realization. So if we let, and this is in the time invariant case, so if I've got my usual set of system equations for the state variable system, and and this is a minimal realization, and I'll write the weighting pattern as g of t. We're assuming we have a time invariant realization, so therefore the weighting pattern is necessarily a time invariant weighting pattern, which means that we can think of it in terms of its transfer function g of s. Okay. Then this weighting pattern is uniformly bounded input, bounded output stable if and only if all of the eigenvalues of A have negative real part. Okay? And this is the condition that we imposed on these uniformly exponential, the exponential asymptotic stability of the state variable system. So if the realization of a time invariant system is exponentially asymptotically stable, then the associated weighting pattern, or equivalently the transfer function, is that way. Right? And g of t is uniformly bounded input, bounded output stable if and only if g of s equal to c times si minus a inverse b plus d has all of its poles with negative real part. Okay. And we should be careful to think about this in terms of lowest terms. So this is a matrix transfer function. It's a p by m matrix transfer function. Given that we have a realization, then that transfer function will be c times si minus a inverse b plus d. So g of s is going to be a rational matrix function, so that every entry of g of s is going to be a ratio of two polynomials. The poles of that transfer function we think of as the union of all the roots of the denominator polynomials of all the entries in g of s. Okay. So the upshot is that G of t is uniformly bounded input, bounded output stable if and only if x dot is equal to ax is uniformly exponentially stable for x dot equal to ax plus bu y equal to cx plus du, a minimal realization. Okay. Questions on that? And, you know, we can go through, if we had more time, maybe we could go through the exercise of actually establishing these facts. It's, you know, the kind of more practice at constructing logical arguments to make statements. But, you know, nonetheless, what we have is it's a nice result, because what it says is if we are able to realize systems, then we can work with the realization of the system and just do this linear algebraic test for stability. We just need to make sure that the matrix A has all of its eigenvalues in the left half plane. And we've kind of already seen that there's something of an equivalence between the eigenvalues of the A matrix and the poles of the system. Right? I mean, if you look at the way that we've constructed these realizations, you know, we find these least common denominators, and we factor the denominators. Those are basically the poles of the transfer function. And we construct A matrices that have those pole locations as the eigenvalues of the system. And the idea of the minimal realization means that we don't have any extra pieces of the realization that don't factor into the input-output behavior. If the realization fails to be minimal, then that means that there's some piece of it that's uncontrollable, or there's a piece of it that's unobservable. And uncontrollable or unobservable parts of the state variable system are disconnected from the input-output behavior, either through there is no connection from the input to the state, that's lack of controllability, or there is no connection from the state to the output, lack of observability. So what we do is we do a realization of this thing. We make sure we don't have any extraneous pieces. So therefore, the stability of the stuff that we have there must impact the stability of the input-output behavior. So that means that we can live entirely within the world of the state variable realizations, right? But we want to be careful that we use minimal realizations for something that we have presented to us only via an input-output description. Okay? Now, stable systems, like stability, is a property that we like our systems to have. So, you know, if you're in some sort of lecture hall and the person's up there, you know, talking away, and you get that big loud noise from the feedback in the microphone to the speaker, that's an unstable system. We don't like that. Right? That's a bad thing, right? If we're driving our car and we turn the steering wheel and all of a sudden the car is going back and forth and we spiral out of control and go off the road, that's an unstable system. We don't like that. We want things to be stable. Right? We would like to have, you know, a bounded motion of the steering wheel result in a bounded motion of the bounded change in the direction of the car, rather than, you know, unstable oscillations. So in a lot of situations, we may be presented with a system, a system that is unstable, and what we want to do is exercise control of the system in order to stabilize it. An example of this that happens is that if you look at high-performance aircraft, like fighter jets and these kinds of things, in order to get maneuverability of the aircraft itself is unstable. And what you do is you, through the exercise of the control dynamics, you restabilize the system. And so you build the thing, its natural dynamics are unstable in order to get, pretty big movements from pretty small actions from the, pretty small effects from the actuators. And then what you do is you utilize the control to make sure that you restabilize the system. So what we're going to do now is look at how we might exercise control of the system through our input U, because if the system's unstable, but also controllable, which it would be via a minimal realization, we ought to be able to utilize our control signal U, or the input signal U, to influence the state in such a way that, the controlled system is stable. Or we might say that, okay, what we have is I don't know, like an elevator. And maybe the elevator is stable, but we want to be able to move the elevator really quickly. And so if what we do is if we apply an input signal to the motor that's kind of pulling on the cable of the elevator car to pull it up, maybe the thing just kind of, we turn the thing on, apply all the juice there, and maybe it just goes. Right? If we want to speed the thing up and be able to move it, get it up to speed pretty quickly and then slow it down pretty quickly, and maybe control other things like the acceleration so that people's stomachs don't go up through their head and when you're starting and stopping the thing. So what we can do is utilize our ability to influence the state via the input to basically reshape the modes of the system. If the original system has an A matrix whose eigenvalues are all sitting at -1, so that we get these terms that look like e to the minus t in the time descriptions for the state and the output, maybe e to the minus t is going to steady state at a time constant that's too slow for us. Maybe we want to speed it up. And if the transients in the response are basically governed by expressions that look like e to the eigenvalue times t, where the eigenvalues are the eigenvalues of the A matrix, if we change the eigenvalues of the A matrix to something bigger and negative, say -10 instead of -1, now those transients are like e to the minus 10t, so that the time constant is 1/10 as big. We make the system faster. And so we have these notions about bounded input, bounded output stability of the system being associated with the eigenvalues of the A matrix having negative real part. If we think of those eigenvalues as complex numbers lying in the complex plane, that means that they have to be in the left half of the complex plane. If they're right on the boundary, right on that j omega axis, we have this, we talked about it as marginal stability before, but essentially it's unstable. If we push it just barely into the left half plane, so it's a very small but negative value, that corresponds to very slowly decaying transients, but at least the transients are not growing as they would even if we had an e to the 0.00001 times t. That thing's growing exponentially, but albeit very slowly. And the further we move the eigenvalues into the left half plane, the larger the size of that negative real part, the faster are the responses of the system. And so if we have a sluggish system whose eigenvalues are, though in the left half plane maybe, pretty close to the imaginary axis, we might want to move them further in by exercising control of the input U. So one way that we can do that is by using state feedback. So if we have x dot is equal to a times x plus b times u, and y is equal to c times x plus d times u, this is our system. What we might do is to say, let's set u equal to some matrix n times r. This could be a reference input. And we'll talk about that as a p by 1 function of time. And so you can think about either controlling the states or controlling the outputs. Right? I've got m inputs, n states, p outputs. So a typical situation where we have a reference input is we say, this is what I would like my outputs y to be. So please make y minus r small. Okay? And we also throw in a minus k times x. This is the state feedback term. And this is something of a feed-forward term. So this is a feedback control law. All right? So here's R. We go through a matrix N to produce an input U, which has an output y, and maybe there's a state x that comes back here, and we feed this back through minus k and bring it up here. And so now what we're doing is thinking of there being a larger system which is going to have internal to it a state x, the same output y, but we'll think of it now in terms of the reference input r driving the system. So we're changing the system dynamics of the original system to a new set of dynamics associated with this controlled system. And we can get a set of equations describing this system in terms of the state x, output y, and input r, simply by substituting this expression for u up here and over here. And if you do that substitution, we get the following equations. We get that x dot is equal to a minus bk times x plus, what do we get? B times n times r. And y is equal to c minus d times k times x plus d times n times r. So we have a new A matrix is A minus B times K. So the question that we're going to pose is it possible for me, if I don't like the eigenvalues of the matrix A, is it possible for me to choose a state feedback gain matrix K so that A minus B times K has the eigenvalues that I want? And what we're going to find is that if the original system is controllable, if the matrices A and B form a controllable pair, then it will be possible for me to choose this matrix K to place the eigenvalues of A minus BK arbitrarily. This is called a pole placement problem, or an eigenvalue assignment problem, or an eigenvalue placement problem. And while we're doing this, I will point out that we have the same thing for discrete time systems. If I have x, k plus 1 is equal to a times x of k plus b times u of k, and I let u of k be equal to, this is a lowercase k, n times r of k minus capital K times x of k, then this results in x at time k plus 1 is equal to a minus b times k times x of k plus bn times r of k. Okay, and we have essentially the same problem here, where now if I don't like the eigenvalues of the A matrix here, I can reposition them to eigenvalues, perhaps, of the eigenvalues of A minus BK. Maybe I can reposition the eigenvalues to places I want, as long as I can set the eigenvalues of A minus BK. The difference is that stability for discrete time systems requires that the eigenvalues of A have magnitude strictly less than 1. And so that's inside the unit circle of the complex plane. So there's a difference in where it is that we want the eigenvalues to be. And for discrete time systems, the closer the eigenvalues are to the origin, the closer they are to 0, the faster the system responds. Okay, in a certain sense, if you put them at 0, if all the eigenvalues go to 0, it's not like you get an infinitely fast response, but you get the fastest possible response. In fact, what happens in that case is that the transients go to 0 in finite time, where even e to the minus 10 billion times t never gets to 0 in finite time. It just gets really close really fast. Okay? So we'll keep the discussion mostly focused on the continuous time systems. But now the question that we're going to pose is, can I choose the eigenvalues, or can I obtain desired eigenvalues for A minus BK by choosing the matrix K? A is n by n. B is n by m. K is going to be an m by n matrix. Right? K multiplies the n-dimensional state vector x. So K times x is, I have this matrix multiplying an n by 1 vector. So I need that right dimension to be n columns. And it's going to produce an m vector input. So the left dimension of K has to be m. Okay. Well, it turns out that if AB is a controllable pair, then the eigenvalues of A minus BK can be set to arbitrary locations or values by choice of K. All right, and so now what we're going to do for the rest of today and for a good chunk of Thursday is to demonstrate the truth of this fact by taking matrices A and B, picking arbitrary values for the eigenvalues, and constructing the matrix K that actually places the eigenvalues of A minus BK at those particular locations. So not only will we understand that we are able to do this, but we'll have a procedure whereby we can get the job done. Okay? And we're going to do this using the single input case. Then we'll look at the multi-input case. And we'll also discuss MATLAB commands. That get the job done for us. And we'll understand a little bit about, or a good portion, a lot about what the MATLAB commands are actually doing when we go through and construct the procedures that affect these things. Okay? All right. So let's look at the single input case. All right, so what we have is x dot is equal to a times x plus b times u. Okay? And u is just a scalar value, or just a 1 by 1, right? So a is n by n, b is n by 1. M is equal to 1. Okay? We've talked about the controllability matrix, B, AB, up to AN minus 1B. And if AB is controllable, or it's a controllable pair, or if we think of the system as being controllable, then the controllability matrix is a full rank matrix. And if the controllability matrix is a square matrix, as it is when we have the single input case, then it's full rank if and only if it's invertible. Okay? Now, if I take B sub c and let it be a vector whose first entry is 0 and the remaining n minus 1 are zeros, I'm sorry, whose first entry is 1 and whose remaining entries are zeros, and A sub c is equal to, let's say, minus alpha 1 out to minus alpha n. And then I'm going to put an identity matrix here. This is n minus 1 sized identity, and I've got a stack of zeros sitting over there. And I'm going to look at the determinant of lambda I minus A. The original A is going to be lambda to the n plus alpha 1 lambda to the n minus 1, etc. So these alphas that I'm putting into this matrix are the coefficients of the characteristic polynomial associated with the matrix A from the original system. And we will let script C sub c be equal to B sub c, A sub c, B sub c, etc. Here's the controllability matrix associated with these two matrices. All right, and this thing here, sorry if I'm getting the camera mixed up, this thing here looks like the A matrix that we used with controllable canonical form, right? A little different, though, because now I have these coefficients on the top row instead of on the bottom row. Things are moved around a little bit. This 1 is at the top instead of at the bottom. So we're not doing it exactly the same way, but functionally it's the same. Okay? And I claim that if I set a matrix P, and this matrix P will be invertible, I'm going to set it equal to script C sub c times script C inverse. Okay? That this takes x dot equal to ax plus b times u to a new system set of equations. Let's say xi dot is equal to a sub c times xi plus b sub c times u, right, via, I got to figure which way I want to go here. Yeah, okay, via a sub c is equal to p times a times p inverse, and b sub c is equal to p times b. Okay. Given that AB is controllable, right, so that script C inverse exists. Okay. In order to define this matrix here, we didn't have to have any requirements on the system. We just took the coefficients of the characteristic polynomial and a bunch of ones and zeros to define A sub C and B sub C, and then put those things together in the usual way to get this to be the controllability matrix associated with this. But if this is a controllable state equation, then its controllability matrix is invertible, given that U is a scalar input. And then we'll look to see what this particular transformation does and show that we get a coordinate transformation for which the A sub C and the B sub C are just a different realization for the same system. Okay? All right. So okay, so we've got x dot is equal to ax plus bu, y is equal to cx plus du. We can get this as y of s is equal to g of s times u of s, okay, where g of s is equal to b0 bar plus b1 times s to the n minus 1, etc., down to bn, over s to the n plus a1 alpha 1, I guess I need, right? Okay? And then from this, I can get a realization z. Z dot is equal to, and the way we did it before was to have the coefficients of the characteristic polynomial be across the bottom. The B matrix looks like this. The C matrix looks like this. And then we have this B0 bar times U. Right? And Z is equal to P bar, I'll call it, times X. Right? So I have this as a, if I put this in lowest terms, then this is a minimal realization. This also is a minimal realization if we're in lowest terms. Okay? Actually, we get a minimal realization as long as g of s is in lowest terms, and this will be a controllable. We get this controllable canonical form if we're in lowest terms. There's no pole zero cancellations. All right, so we know there exists a coordinate transformation between them because they're both minimal realizations. And what I can do is to define this xi as a matrix of mostly zeros, but I put ones on the anti-diagonal. And all this does is to reorder the last element of z becomes the first element of xi, the first element of z becomes the last element of xi, and vice versa. Okay? So therefore, xi is equal to this permutation matrix multiplying z, which is p bar times x. Okay? And so this is my matrix P. Okay? So there exists a transformation that goes there. And C, which is B, AB, AN minus 1B, script C sub C, which is B sub C, A sub C, B sub C, out to A sub C, N minus 1, B sub C. And B sub C is equal to P times B. A sub C is equal to P times A times P inverse. Okay? So therefore, script C sub C is equal to P times script C. And if I take these values and just substitute them in here, I get P times B here. I get P A inverse, or I get P times A times P inverse times P times B. The P inverse and the P inverse and the P cancel. So this is P times A times B. And then this thing is going to be P times A to the n minus 1 times B. So this matrix is just P multiplying C. So therefore P, if I multiply both sides by the inverse of the controllability matrix, then that gives us the transformation matrix that takes us over to this new set of coordinate systems. Okay? So now what we have is we can transform coordinates so that we have xi dot of t is equal to minus alpha 1 out to minus alpha n, an identity matrix, a stack of zeros, times xi of t plus 1 and a bunch of zeros, times u of t. Okay? And what I'm going to do is to consider what happens if I let u of t be equal to, I'm just going to write this as minus k sub c times xi of t. Okay? Where I'm going to write k sub c is equal to k1 sup c, k2 sup c, k sub n with the superscript of c. We'll just push the c up in the superscript just so it stays out of our way. And we'll try to spell where correctly as well. Okay? So you can think of this, suppose we're given the A matrix in this form and the B matrix in that form. If we're not, what we can do is transform the system using this coordinate transformation matrix P equal to script C sub C, based on these matrices, times the inverse of the controllability matrix of the other system. We can put the matrix in this form, and then we can define the control input U in terms of state feedback of the transformed state. All right, we'll go back to X in a moment. But we can do this. Now, I've left off the R term. If you look at the equations, I think they're up here somewhere, maybe. No, they're all gone. But what we had was X dot is equal to A minus BK times X plus B times N times R. Right? So if we have the N times R term, that'll affect these other matrices. But the matrix involving that we're trying, whose eigenvalues we're trying to shape, it doesn't matter what N is. So we're just going to leave N out of the picture. We can add it in later. Okay? Now, here's A sub C. Here's B sub C. And if we look at A minus BK, right? Here's the matrix A, or A sub C. Minus B times K. That this is if I multiply this out, I get K1C, K2C across to KNC on the top row, and then I get a bunch of zeros down below, right? 1 times this goes there, 1 times the second one goes there, 1 across, right? And then it gets 0 times this goes here, 0, you know. And this then is equal to minus the quantity alpha 1 plus K1C minus the quantity alpha 2 plus K2C minus alpha n plus KNC. Right? I get an identity matrix here, and I get a stack of zeros down on the bottom. So this is the matrix A sub C minus B sub C times K sub C. This is what we call a companion form matrix. We constructed this matrix from the coefficients of a characteristic polynomial. And what we know is that if we take the determinant of lambda times the identity minus this matrix, that we get that characteristic polynomial back. So this is a companion matrix to the polynomial. So what we know is that the determinant of lambda I minus A sub C minus B sub C, K sub C is equal to the polynomial whose coefficients show up along the first row. That's K sub 1, see? Right? So, if we want this characteristic polynomial to have particular roots, that lambda I minus A sub C minus B K, this thing here, the determinant of this is equal to lambda minus R1 across to lambda minus Rn, right? If I have n different roots and we multiply them out, okay, and this is going to be lambda to the n plus, what do we want to call this? Let's say I guess A1. I guess we can use A1. I used alphas over there. Lambda to the n minus 1, etc. over the AN. Then setting alpha 1 or alpha I plus K sub I C equal to A sub I for I equals 1 up to n, which says that K sub I C is equal to A sub I minus alpha I. This will work. So I take the coefficients of the characteristic polynomial that I have for the original A matrix, take the coefficients that I want for the new A matrix, subtract the old polynomial coefficients from the new polynomial coefficients, and those give me the values that I want to put into the state feedback gain matrix K sub C for the state in these transformed coordinates. Okay. All right. A sub C minus B sub C K sub C for that choice is equal to minus A1 minus A2 out to minus AN with an identity matrix and a stack of matrix zeros at the end there so that we get the proper companion form matrix. Okay? Furthermore, if we set K equal to K sub C times P, then A minus B times K is equal to, well, A is the matrix. We go to A sub C using this transformation matrix P. So we can go from A sub C back to A using a transformation matrix P inverse. Right? So this is the same thing as A. And then B is P inverse times B sub C. And then I multiply by K. And let me A minus BK is then P inverse A sub CP plus P or minus P inverse B sub C. That's B. K is K sub C times P, right? Which is equal to P inverse times A sub C minus B sub C K sub C times P. Right? So that A minus BK shares the same eigenvalues with A sub C minus B sub C K sub C. All right, so it turns out also that if you look at script sub C inverse, it turns out to be 1, alpha 1, alpha 2, down to alpha n minus 1, 0, 1, alpha 1, etc. P inverse is equal to script C times script sub C inverse, okay, which is equal to script C times this matrix. Okay. So K is equal to A1 minus alpha 1 out to AN minus alpha n times the inverse of this matrix times script C inverse. So here's a formula for a state feedback matrix K that produces A minus BK with characteristic polynomial whose coefficients are these A terms, given that the characteristic polynomial for the original A matrix were the alpha terms. And this is a matrix constructed from those polynomial coefficients. And this controllability matrix just comes from B and A. Okay? Okay, I have a numeric example here that I think I'm going to skip. All right, via MATLAB, so if A and B and let's say we set P equals P1, P2 to Pn is a vector of desired eigenvalues, then what we can do is let K be equal to place for eigenvalue placement or pole placement. We say, all right, I've got an A matrix, I've got a B matrix, and I've got a vector of desired eigenvalues, and it will compute the state feedback gain matrix K determined by the particular formula that we've written down. There's also a command acker, which is short for Ackermann. And the expression that I wrote down over there in the red box is what's known as Ackermann's formula. Now, it turns out that Ackermann's formula is numerically a little sketchy at times. And so place works better than Ackermann. Place works better than Acker generally. And I think sometimes what happens is place will fail to work as well sometimes. They can run into some numerical issues. But MATLAB generally tells you when you need to worry about the numerical problems. Okay, this requires A and B to be controllable. Right? The formulas don't work. Well, the formulas may not work if A and B fail to be controllable. So let's look at what happens if A and B are not a controllable pair. So if these aren't controllable, then that means that there's a transformation of the state space over to, say, a new coordinates, which I'll call x1, let's say, where the A matrix has the form with a big bunch of zeros down in the lower left, and the B matrix has a form of a big bunch of zeros down in the bottom. So what we can do is do a transformation that exposes the lower portion of this state vector as the states that the input is not able to influence. It's not able to influence them directly, nor is it able to influence them through the portion of the state space that it can affect directly, right? And so in this particular case, if U is equal to, let's say, R minus K1 times X1, okay? Let's say K times, I'll just leave it as K. Let's write this as R is equal to, or R minus, let's say, K11, K12 times X11 and X12, where I partition the matrix that way. Then what we get is X11 dot and X12 dot is then equal to A11, A12, 0, A22. Here's the A matrix minus B times this matrix. We're going to get B and the K11, K12, right? All this times the X11 and the X12, right? Plus B1 times R. This here is B1, K11, B1, K12, 0, 0. Right? So when I subtract this from this, I'm going to subtract 0 from the 0 over there. I'm going to subtract 0 from the A22 over there. And we look at the equations, and what we get is X1 dot is equal to A11 minus B1 times K11, A12 minus B1 times K12, 0, A22 times X1 plus the B10R. We don't have to really worry about that. We're just focused on this piece. And here, the eigenvalues are the eigenvalues of A11 minus B1 K11 and the eigenvalues of A22. So there's a portion of the A matrix that we can't affect, and whatever the eigenvalues associated with that portion are, they remain as eigenvalues of the system that we get with state feedback, regardless of what the state feedback gain matrix is. We just can't change those eigenvalues. And we've remarked that with that coordinate transformation, the pair A11 and B1 is a controllable pair, so we'll be able to arbitrarily assign the eigenvalues of that portion of the A matrix by choice of K11. K12 doesn't matter. Okay, so if the system is not controllable, we're still able to shift all the eigenvalues of the portion of the state space that lie in the controllable subspace, and we're not able to influence the eigenvalues of the portion of the state space that lies outside that controllable subspace. Okay? All right. Now, we've got 5 minutes. I want to make use of my 5 minutes and set up for next time the multivariable case, which is a little more complicated. Right? A is n by n. B is n by m. K is going to be m by n. Right? And what we want is to find K so that the determinant of lambda I minus A minus BK is equal to lambda minus lambda 1, lambda minus lambda 2, right? We have this product of a bunch of terms where we've got these desired eigenvalues. Okay? We're going to make some assumptions that are not limiting. One, I'm going to assume that the rank of B is equal to M. All right? That means that the number of inputs can't be bigger than the number of states. If I have more inputs than the number of states, there's a little bit of overkill there. Okay, furthermore, I don't want to consider the case where I have any extraneous inputs, in the sense that if the rank of the B matrix is less than M, then there are columns of B that are expressible as linear combinations of the other columns. And so that means that there's some input whose actions can be replicated by an appropriate linear combination of some of the other inputs, and they don't give us any extra capability to control the system. Right? So that'll simplify a little bit the exposition, and it doesn't cause us any loss of generality, because if the rank of B is bigger than M, then I've just got kind of overkill on my inputs. And we'll also assume, as before, that the system is controllable. Okay. All right, and what we're going to do is find K by first transforming x dot equals ax plus bu to, let's say, z dot is equal to fz plus gu, all right, where f and g are in what we call controller form. Okay? And what f and g are going to look like, f is going to be something that has, the upper left is going to look like this. I'm going to have a stack of zeros and an identity matrix of some size. All right? And then on the row immediately below this, I'm going to have a whole bunch of stuff. I don't care, you know, this row can be anything. All right? And then I come down, and just over here, I've got another stack of zeros in an identity matrix, and that might be a different size block than this. And on the row below that, I've got a bunch of stuff. Okay? And this continues until finally down here, I have the last of these blocks. And the last row is just a bunch of stuff. Okay? And everywhere else, I've got zeros. Okay? So it's kind of like, you know, if you look at this, this is going to be a companion form matrix. This is going to be a companion form matrix. And so the entries that sit just below these special blocks are going to be associated with coefficients of characteristic polynomials. Okay? Actually, they're not. What I'm going to do is I'm going to put zeros and stuff there. But it has that kind of structure. Okay? And the G matrix is going to parallel this form. Let me write it this way so we can line things up. Then I'm going to have a bunch of zeros and then a 1. right? And that 1 is going to sit on the corresponding row to all these, whatever those values are. Okay? And then to the right of that is, who cares? And then just over from this is another stack of zeros and a 1, okay, where that 1 corresponds to the next non-trivial row. And then to the right of that is whatever I get there. And this is going to keep going down until I get finally, on the last column, I'm going to get something corresponding to this. So the number of these block sections in the A matrix or in the F matrix is going to correspond to the number of inputs, M, that I have. Okay? And everything else in this matrix is a bunch of zeros. This is, okay? So we're going to do two things. One, we're going to show that we have a coordinate transformation matrix P that takes us to controller form. And then once we have controller form, we'll be able to write down an expression for the K, the feedback gain K matrix in controller form, that makes F minus G times K be what I want so that the eigenvalues are all in the right places. All right, that's what we're going to do next time. We're done with today. See you in a couple days.